Thank you very much to the organizing committee for the opportunity to present you here today PAT tools, control strategies, and disturbance prediction for continuous manufacturing of solid dosage forms. So I am Ildiko Terebesi from Invite, and I have the privilege to present here the data of Annika Wilms and Moritz Peterwitz, who are until recently PhD students at Invite in the group of Werner Hocheisel. Now, before jumping into the topics, I would like to introduce you briefly Invite and the Drug Delivery Innovation Center at Invite, and then present you the most recent data. First, in the case of PAT inline measurement of the granule size distribution in a continuous dry granulation process. And then in the second part, to introduce you to the concept of disturbance prediction in a continuous tableting process. Now, who is Invite? Invite is a public-private partnership of Bayer with the two universities of the Technical University in Dortmund and the Heinrich Heine University in Düsseldorf, and was founded in 2010. We are a research center with a focus on innovative production technologies, and are also hosting and leading the Drug Delivery Innovation Center. The Drug Delivery Innovation Center is an open consortium between industrial partners from the pharmaceutical industry, but also equipment manufacturers and academic partners, meant as a pre-competitive consortium doing research on drug delivery. You see here now our main industrial partners. Next to Bayer, also Merck and UCB are in, and they are the three big industrial partners also financing all of the work of the DDIC. But the communities are mandated by the tier 2 partners. As mentioned, excipient suppliers are among them, but also equipment manufacturers and other service providers. And the academic partners also here, beyond our two shareholders, the TU University in Dortmund and the Heinrich Heine in Düsseldorf, also the Ludwig Maximilian University in Munich is associated, and the University in Greifswald. And as mentioned, the consortium is led by Invite, and all the data I present you now in the next slides was done in the frame of the DDIC and represents a part of the work, which goes, of course, much beyond of what I can present you today here. But now jumping into the topic, in the first one, the PAT inline measurement of the granule size distribution in the continuous dry granulation process. You see here on the slide in the middle a picture of the equipment. It's a VRC25 roller compactor from the company LV Bohle, which kindly was offered us the opportunity by Bohle to use this equipment there at their site. On the left-hand side, you see now a schematic overview of the process. And the number one is the powder inlet. And I would like to draw your attention specifically on the impeller, which is also shown there, because you will see later on the importance of this piece of the equipment. The powder is then further transported by the feeding auger and the tamping auger to the rolls, where in fact the compaction occurs and the ribbons are produced, which are then further transported to the conical sieve. In the schematic, it's the number 6. And here in the sieve, then the grinding of the ribbons occurs so that the final granules are received. The inclusion of an inline laser diffraction unit into this setup enabled the in situ measurement of the granule size distribution of the product. And the granule size distribution is a critical quality attribute of the granules. For example, when thinking of the further processing, the flow characteristics are strongly determined by this. If the next step would be a tableting process, for example, the dye filling is dependent on this, or if the granules are your final product, then for sheet filling. Now here you can see how this inline measuring tool was attached to the roller compaction unit. You see it on the right-hand side. And the laser diffraction unit was from the company InZtech and had a 500 millimeter focal length and a 670 nanometer red diode laser and a scan rate of 2000 Hertz. So upfront, the maximum throughput, which could be effectively measured, as well as the reaction time of the tool after a process change, for example, when changing the specific compaction force, was determined, and it was proven that the reaction time of the laser diffraction tool is reasonably fast. So it was just about 15 to 30 seconds for the D50, and thus enabled to build a reasonable control strategy based on this measurement. So here on the next slide, now you can see the real data as measured by the tool and how the granule size distribution changed in dependence on the specific compaction force, which is the green line, showing the changes in the compaction force. And the constant level of the particle size is reached after the specific compaction force and the gap width had reached an equilibrium. And an excellent response of the granule size distribution to the specific compaction force was proven by the data. And it could be also shown that changing back to a previous specific compaction force led to comparable results in the granule size distribution, thus proving that the setup can generate reproducible results and is suitable to monitor the process. So thus the question to be answered was, can a control loop be established based on the monitoring of the granule size distribution? So to confirm this, experiments were conducted at a constant specific compaction force, but change in the gap width. As you see here, in the part 1, the gap width was 2 millimeter, and in the second part, 2.5 millimeter. And as expected, a drop in the granule size distribution was seen. Here you can see it on the blue line. And a control mechanism for the granule size distribution with a feedback loop was established now via a counter-regulation of the impeller speed, what I showed you in the sketch previously. So the results after implementing this feedback and counter-regulation loop, you can see now here. And the results proved that the drop in the particle size can be counter-regulated by the controlled adjusting of the impeller speed. So the red curve here shows the variable impeller speed dependent on the current granule size. So the drop in the granule size at minute 17, so just after the adjustment of the gap width, is directly counter-regulated by a sharp decrease in the impeller speed, as you see it on the gray line. So therefore, even at increased gap width, the desired granule size was maintaining what the red line shows. So overall, control of the granule size distribution via a counter-regulation of the impeller speed could be established. And in comparison, what you see here in the graph is that even a less aggressive controller set, as shown here for KT 0.5, was sufficient to effectively control the granulation process and to prevent an overregulation. Similarly, as shown here for the feedback and counter-regulation loop via the impeller speed, it was also proven that control loops could be established also for the specific compaction force as a controller, and also the gap width as a controller. I just do not show the data here due to the time constraints. However, overall, the control via the impeller speed is the most favorable one from our perspective, as the change in the specific compaction force or the gap width do impact further critical quality attributes, and also the fact that they themselves belong to the critical process parameters and are controlled themselves also impedes their use for counter-regulation for the granule size distribution to a certain extent. So overall, to summarize this part, what we achieved is to establish an inline determination of the granule size distribution via an inline laser diffraction unit into the process, and proved this to be suitable up to more than 15 kg per hour production speed. And this enabled us to establish a control strategy and a counter-regulation loop, which could be proven also for the impeller speed control, specific compaction force control, and the gap width control, of which the impeller speed control is the preferred one. So open questions are the evaluation of the reproducibility, but also the sensitivity to other process parameters such as humidity, for example. Now turning to the second part, how disturbance prediction in a continuous manufacturing process could be established. When thinking of how manufacturing in the pharmaceutical industry was in the past, then this was conducted batch-wise in a series of separate distinct process steps, and thus turning towards continuous manufacturing offered, of course, many advantages, among them the reduction in space requirements, but also leading to a more constant product quality. However, the challenges coming with it are due to the axial backmixing in this process, which leads to batch transition areas, so we don't have these distinct batches anymore, and due to this, then also propagation of disturbances throughout the process. Now, in a given process, critical process parameter is a process parameter at the entry to the process, which has potentially a direct impact on the product quality. So here for the tableting process, for example, the drug content in the bulk granulate. It is measured at the entry of the respective process, and the critical process parameter has a direct correlation to the critical quality attribute of the final product. So in this case, then the drug content of the final tablet. So a disturbance in the CPP thus has a direct impact on the critical quality attribute. Now, weak disturbances in such a process could be caused, for example, by fluctuations in the feeding, dosing inaccuracy, or release of adhesions, while strong disturbances occur due to a malfunction of the equipment. Now, in this context, the residence time distribution is used as a measure for the degree of backmixing in the whole process, and the residence time distribution represents the time-based probability of the material to leave the system, which can be evaluated, for example, by tracers. So subsequently, an incoming disturbance and the residence time distribution can be convoluted. And as the critical process parameter has a determined relation to the critical quality attribute at the end of the process, the impact of such a disturbance can be predicted based on the residence time distribution, and the amount of product out of specification can be then directly predicted and discharged as a deviation point related to this CQA. But the question is, what is a minimal degree of backmixing needed to enable an efficient smoothing in case of weak disturbances and preventing thus a discharge of the material? But on the other hand, also, how do we ensure that disturbances causing an out of specification are reliably determined? So this question was systematically addressed by a statistical experimental approach, as you see it on this slide. So step change experiments were conducted, and the tablet content was analyzed by UV-Vis. And based on this design of experiments, plan the impact of the operational parameters, such as the turret speed, the feed frame speed, and the hopper filling degree were investigated, and a residence time distribution model based on regression could be established. So a statistical evaluation of the model parameters and correlation to the operational parameters enabled the prediction. Now, when looking on this slide, how the critical quality attributes are interrelated to the critical process parameters, then based on empirical correlation, the critical quality attributes as laid down in the specification can be transferred to the critical process parameters on the left-hand side. So based on the correlation between the CQA to the CPP, the amplitude of the disturbance in CPP still matching the specification limit can be calculated. And thus, the lower boundary for the CPP, the LV CPP, represents the limit for occurrence of out-of-specification product. This means that as long as the CPP in the process is below this lower boundary of the CPP, the product will always be within the specification, and the LB CPP is correlated to the specification limits, including a safety margin. Now the safety margin comes, for example, that for the empirical correlation, not the set point for the normal material was used, but the out of control limit, which is the worst case assumption for the critical process parameter value of the normal material. Now, based on these considerations, we tried to determine a criterion for the minimal degree of backmixing needed when considering short-term disturbances. So at such disturbances, the related question arises how to determine a sufficient measuring frequency. Ultimately, any disturbance that causes out-of-specification material must be detected reliably. However, the stronger the disturbance, the more likely it is to cause out-of-specification material, even then if it's just of a short duration. So therefore, worst-case disturbances that were assumed to be the strongest possible were considered here. The high measuring frequency is especially needed to detect all disturbances of a specification relevant duration. So that's what you see in the graph on the right-hand side. So in turn, we calculated the longest duration of the disturbance causing no out-of-specification material, and consequently, all disturbances of a shorter duration than this do not need to be detected with absolute certainty by the measuring tool, as they are not relevant. They cannot lead to out-of-specification material. So thus, this duration can be used to calculate the minimal measuring frequency needed. However, the smoothing of short-term disturbances depends on the degree of backmixing, and thereby the frequency calculated is a measure for the backmixing. So this relationship can be also inverted, and we define our minimum degree of backmixing based on the available measuring frequency of the PAT tool, which we just have at hand. In other words, the backmixing must be strong enough to smoothen out all disturbances potentially not detected with the available measuring frequency of the device available. So on the next slide, you see now this criterion, how for the minimal degree of backmixing, how it was applied to the RTD model of the tablet press and the required measuring frequency calculated out of this. So the results proved that the minimal needed measuring frequency of the tablet press is already much lower than the available frequencies, for example, by near-infrared measuring tools. So to conclude on this, the degree of backmixing in the tablet press is sufficient to smoothen out all undetectable disturbances, which is great. So, and adjusting the operating parameters further reduces yield losses by more than 30%. And backmixing in devices upstream of the tablet process, especially in the feeder, could and should be further reduced to decrease the size of the batch transition interface and other losses due to backmixing, and thereby also to further reduce the amount of discharged material. So with this, I'm at the end of what I wanted to show you today, and I thank you very much for your attention. But also, importantly, I would like to thank all other colleagues who supported this work, especially to the professors at the universities. So for the first part, it was from the Heinrich Heine University in Düsseldorf, Professor Kleinebuder. And for the second part, it was from the Technical University in Dortmund, Professor Thomas and Professor Schembecker. And of course, we are grateful to LB Bohle for the opportunity that we could conduct all of these experiments on their equipment. So means with real life equipment and have these valuable results. And finally, to thank Ashland Industries who supported us with generous provided excipients. So finally, I thank you for your attention, and I'm looking forward to questions either now during the conference or also later on. Anytime you have here our contact details. Thank you.